Right, so in the previous video we saw that a capacitor would block DC and an inductor would pass DC. Direct current, frequency equal to 0. So that's fine, and the DC world is really something which tends to be taught at high school. Why? Because life is considerably easier at DC, in other words, like a battery, plus and minus, it doesn't change over time. But life gets really interesting where voltage and current change as a function of time. In other words, they're a waveform. And an alternating current will have a period and it will have a frequency which is equal to 1 upon the period. What that means is that I can increase the frequency of the AC waveform. In other words, if we assume that's a relatively low frequency, we can make the frequency higher by having more cycles per second. And obviously that's measured in the magic hertz, from the German. And we can say how many cycles, and that's a cycle. Let's just use a different colour and hope it comes out. So a cycle is from this point here to this point here. So the same point on the wave, basically. So how many of those points pass per second, that's the number of cycles in hertz. Okay, fine. So let's go back to the thing that we did originally. And so we've got a voltage source, we have a capacitor, and we have a load, and we have an AC signal here. What happens in this case is, obviously when this goes plus here, that's going to go plus here, it's going to induce a little negative sign on the other side of the plate. And as this goes minus here, it's going to go minus here, which is going to pull a little bit of plus on the other side of the plate. So the plus and the minus which is happening on this side of the plate, there's also going to be a plus and minus on the other side of the plate, even though there's an air gap between them. So that means AC current is going to flow through the capacitor. So we're actually going to have real current flowing through that capacitor as the other side of that capacitor goes plus minus, in the same way, but out of phase, but in the same way as it does from the original AC voltage source here. Now, one of the equations which you may well have seen in high school is that XL, which is the inductive reactance of the capacitor, in other words the equivalent resistance it has, is equal to 2 pi FL. For the inductor, we're getting ahead of ourselves a bit here, I'm just going to put a cross through that for the moment. So XC is equal to 1 upon 2 pi FC. That's the one for the capacitor, that's the one for the inductor, but I've just taken that out because we're doing capacitors first. Now what does that tell me? What that tells me, so this is equivalent resistance, or impedance, because it's an alternating current. What that tells me, well, think about it. 2 pi, that doesn't change. Capacitor, that doesn't change for the experiment, unless I change the capacitor. F can change. So what does that tell me? So that as F gets big, what does the impedance look like? Well, it's 1 divided by a big number. So as F gets big, XC gets small. And as F gets small, XC gets big. So in other words, we have something which is frequency dependent. So that capacitor is going to have a different impedance, resistance, but impedance, is going to have a different impedance at different frequencies. Well, that's marvellous. So before we were saying that we want something that either lets current flow through or blocks current. Now we can have current passing through or current blocked, and we're in control of it, because either we design a circuit in a particular way that we can design the frequency at which we let that current through, or we can dial up the frequency that gives us the results that we're looking for. We have frequency dependent resistance, or impedance, but resistance for the DC case. So that's quite clever. That's quite clever. So we've got the same argument for the AC waveform, but what we can do now is we can say, well, let's do the same thing. I'm just going to move up because you can't see at the bottom of the page. My tripod. So we've got an AC waveform, and this time we have an inductor. We have a load because we need a load to complete the circuit, and we've got V there. So the equation, which I crossed out up here because I didn't want to cause confusion there, but is XL, the equivalent resistance, AC resistance, is equal to 2 pi FL. Now you'll see some indication of where these equations come from in a minute when I go back to first principles and do a little bit of calculus, but I don't want to confuse the matter too much. So XL is equal to 2 pi FL. Let's do the same as we did here. Let's just draw a box around this. So this is for capacitor. Apologies for my page planning. I could have planned the page a little bit better. I could have just used a bigger piece of paper, but I didn't. So XL equals 2 pi FL. What that means, as F gets big, remember 2 doesn't change, pi doesn't change, the value of the inductor doesn't change. For the same experiment I can change the inductor, but as F gets big, XL gets what? Well, XL gets big, because if F goes to a million, a billion or whatever, XL is big. So XL gets bigger as frequency gets bigger, and as frequency gets small, XL gets small. So what's that telling us? As we increase the frequency, the inductor will block. As we decrease the frequency, the inductor will pass the current, which is completely the opposite to what we see at the top here. Because as the frequency increases, the capacitor will pass the current, and as the frequency decreases, the capacitor will block the current. Isn't that neat? Just another box around there as well. So this is the inductor. Okay, more to come.